Hello everyone, this is HICHAM speaking. Today we're gonna have a talk about how to develop and improve electrochemical sensor for catechol detection. But before we start, please let me share with you the plan of our presentation. So through quick introduction, we're gonna dig deeper in the subject by speaking briefly about electrochemical science and nanotechnology. And then we're gonna go to talk a little bit about how we can synthesize new hybrids, new nanomaterials. And of course, at the end of our presentation, we're gonna discuss more the electroanalytical performance of the fabricated sensor before we come up to some important conclusions. To understand better the subject, we should ask three very important questions. What for, and why? What is a sensor? What this sensor is used for? And why we are interested about developing a sensor. So briefly, a sensor is any analytical device that could transform a chemical or electrochemical or biological reaction into electrical signal. And this sensor for sure almost applicable in everywhere, so we can find sensors in medical science, environmental monitoring, food science, almost everywhere. The key features of any analytical sensor is fast, stable, cheap, and easy to use. That's why it's very important to develop sensors, because they are very important compared with other analytical tools. As typical example of sensor, we find glucose sensor. We almost know a person who is diabetic person. So for sure you have seen this electrode before. This electrode called screen printed electrode. It contains 3 electrodes and counter, reference, and working electrode. The working electrode is where the reaction occurs. As you see here, for example, in our case, catechol will be oxidized on the surface of the sensor. And this oxidation reaction will be converted to electrical signal using transducer, and this signal will be amplified and then processed inside electronic device, and at the end will be processed on its screen. Basically, in the laboratory we use similar 3 electrode system. So as you see here, the role of the reference electrode is to maintain constant potential between the working electrode and the reference, and the counter, it has a very important role to close the circuit and to flow the current between the working electrode and counter. So the most important electrode here is the working. Why? It is very important because on this surface the reaction will occur here. But there is an issue here, that this surface isn't really efficient, especially if we do analysis. That's why we need to overcome this issue. The solution proposed here is to modify this surface using some specific nanohybrid or nanocomposite or any other nanomaterial. So to do so, we have to pass through 4 important steps. The first one is the synthesis of the nanohybrid. Here in our study we have synthesized an organic-inorganic hybrid, but before we go further with it, we need to do some physicochemical characterization to see if we successfully synthesized a desired and good conductive nanomaterial. Once we have done, we go to the next step, the modification of the glassy carbon electrode. Why we're going to modify it? To improve its surface and electrocatalytic activity, of course. At the end, to measure and to assess the performance of the sensor, we have to do some electrochemical analysis using cyclovoltammetry technique, using different catechol concentrations. In this work, we have successfully synthesized a new organic-inorganic hybrid based on treated carbon nanotubes. So the treatment of the carbon nanotubes passed through an acidification process using nitric acid and sulfuric acid. To check and evaluate the morphology of the nanohybrid, a scanning electron microscopy analysis was examined. As you see in the left of the screen here, the carbon nanotubes has a well displaced porous surface due to the acidification process, of course. But if you compare it after the incorporation of zinc oxide nanoparticles on its surface, you can see that there are a deformation on its surface, and it had a shrinking phenomenon here, and walls were created on its surface like honeycomb structure. Also, we can notice clearly some white points indicating the presence of metal, which is zinc oxide, on its surface. Another analysis was examined also to evaluate the functions presented in the synthesized product or the synthesized nanomaterial. Here you can see the causal peaks that may be presented in any other carbon nanotubes, but we are interested here about this peak due to the hydroxide group that came from the acidification process. So we can say that we have successfully treated the carbon nanotubes. Now, if you see the second spectrum, if you compare the zinc oxide, zinc nanoparticle oxide functionalized with carbon nanotubes, and the first one, you can see that almost same peaks are presented here. The only difference between both of them is this vibration around 500. This vibration is due to the zinc oxide nanoparticles. So we can say that we have successfully doped the zinc oxide nanoparticles on the surface of the carbon nanotubes. So to go further and do the electrochemical measurements, we need to use a potentiostat that it is connected with 3 electrodes here. The red one is the working electrode, and 3 electrodes are immersed in electrolytic solution that contains a PBS solution and the analyte, which is catechol in our case. But before we launch our experiments, we need always do a preparation to the glassy carbon electrode surface through polishing as first step using alumina slurry. And then, of course, we're gonna wash it using deionized water and ethanol to clean its surface, to make it ready for modification. So to modify this surface, we need to use a micropipette to dope a microvolume here of colloidal solution of the synthesized nanohybrid. Now, if you see here, this solution before using sonication and here after sonication. As you see, this one is more homogenized solution. So we have used this one to modify the surface of the electrode. Now, as you can see here in this cycle voltammetry diagram, the black one is the bare electrode. The analysis here was occurred in 0.1 molar of PBS, including containing 5 millimolar of catechol. You can see that the bare electrode in black can barely detect the presence of catechol in the solution, contrary to other modified electrodes. If you compare again between the second and the first one, you can see that the hybrid is more effective compared with carbon nanotubes alone, and this due to the presence of zinc oxide in the nanomaterial. So if you see here, you can see clearly the difference between the bare electrode and the modified electrode. It's almost 5 times better than the bare electrode if we modify it. So for the next sections of our work, we're gonna use the hybrid zinc oxide functionalized with carbon nanotubes for our next studies. To simulate the system, we can find charge transfer resistance and capacitance on the surface of the electrode, and of course we're gonna find also solution resistance as long as the surface of the electrode is in contact with the solution. So if you can see here in the table, there is a decrease in the charge transfer resistance if you compare the bare electrode and the modified electrode. And this is the most important thing in our work, is to decrease this resistance and at the same time increase the system capacitance to make the sensor well performance. So to check the performance of the sensor, the first thing we should do is to evaluate and to assess the diffusion on the surface of the sensor. To do so, we have changed the scan rate from 10 to 500 millivolts per second, and as you can see, there is a linear relation between the scan rate and the current flow. Each time we increase the scan rate, an increase in the oxidation peak and the reduction peak were occurred. So the linear relation between current and diffusion is verified here in our case. So we can say that the electron transfer process on the surface of the electrode is adsorption control toward catechol. To obtain the analytical parameters of the sensor, we have done a detection experiment using different concentration of catechol. As you can see, each time we increase the catechol concentration in the solution, we had an increase in the oxidation peak. So the sensor showed a wide linear range from 10 to 100 micromolar. After 100 micromolar of catechol, the sensor lost its linearity. So we can say that catechol sensor, or the fabricated sensor here, has a wide linear range from 10 to micromolar. To determine the other analytical parameters, limits of detection for example, we used these equations using MATLAB or Excel to find them. So the sensor showed lower LOD around 11 micromolar and also a lower limit of quantification around 35 micromolar. Now, do you think the sensor is highly performant one or not? To say so, we need to do a stability and reproducibility and of course a repeatability test. So to check the stability of the sensor, we have done 30 CVs, 30 success CVs, and before 20 CVs. Let's focus on 30 because as you can see, it was stable in 20s if we compared with 30 CVs, and here the stability was around 91%. So we can say that our sensor is stable. To check its reproducibility, 5 electrodes were prepared using different electrodes using different hands, and as you can see, the results are almost same with the relative standard deviations around 6%. So it is acceptable results. We can say that our sensor is reproducible. To check the repeatability, we kept the same conditions, same modification, same electrode, and we repeated the experiment 7 times. And as you can see, the RSD here is neglected, is around 0%. So we can say that our sensor is stable, reproducible, and repeatable. So before we finish our presentation, let's summarize what we have seen here in this work. We have successfully proposed and developed a sensor which is stable, sensitive, and reproducible also. We have talked also about the effects of the modification of the surface using the nano hybrid and how it was really effective in improving the sensor electroanalytical performance. So if you are interested about the work, if you have some inquiries, please do not hesitate to contact me throughout this mail. So thank you so much.